so this time I'm going to bring a slightly different perspective to the proceedings. So what I want to tell you about is string diagrams. So string diagrams are a different way of notating natural transformations and functors. So probably not this time, but next time I want to show you how it looks very funky when we go to monads and adjunctions, and how everything works out wonderfully. So I'll just introduce you to them this time. So what is the idea of a string diagram? So traditionally, if you've got a functor between categories, so we've got a category C and a category D, then you might write a functor between them like this, capital F there. So what we want to do in string diagrams is take what the topologists would call the Poincare dual of this. So we replace dots by lines and lines by dots. So let's look. So something that looks like this. So this is supposed to be D, and this is supposed to be C, and this is supposed to be F. Okay, so that's looking pretty dull so far, not terribly interesting. So the important thing to note at this point is that I'm coming from whatever that side is to whatever this side is. Okay, so we'll see that this makes sense when we're doing composition. So why is this a sensible thing to do? So when we compose, so if we do a functor F and then a functor G, we're going from C to D to E, that is supposed to be equal to the functor FG. Sorry. It was exactly to avoid having to switch the order that I'm coming this way. So the point is that I don't have to switch the order. So that means do F first and then do G. So we look exactly the same way around. So that's why I've decided to orient things in that direction. So to stop me making that mistake. So here we would just have, if we do E, D and C, and we've got F and a G there, so that's just supposed to be the same as something like. Okay. So it's looking pretty dull here. It's not very interesting on functors. It's going to get far more exciting once we get to natural transformations. So I'm not controlling my board very well yet, because I'm going to have to rub this out. So that's the gist of functors, but it's not very good, not very interesting there. So let's see what happens when we get to natural transformation. So the traditional way of drawing a natural transformation, again, I might go contrary to other people's conventions. So if I have a functor, I have a functor F and a functor F primed, and I have a natural transformation between them. So that natural transformation is theta, and I'm going from C to D, then again I'm going to take what's called the Poincare dual, which just means replace. So this is a two-dimensional thing. So now we're working in before we were working in one dimension, so zero-dimensional things went to one-dimensional things. Now we're working in 2 dimensions in the whole of the plane. So zero-dimensional things get changed into 2-dimensional things. One-dimensional things stay one-dimensional things, and 2-dimensional things become points. So in our string diagram language, we would notate this. We're just going to be sitting inside a plane. So the little dot there becomes the whole of the region here on this side. The F becomes a line, and then the theta becomes a point, and then the F prime becomes a line at the bottom here. So we've got F prime, we've got a C, and we've got a D. And we've got a theta. Now, the important thing to note is that if you look down at the bottom here, we have the thing that I encoded on the last blackboard for the functor F. So it's just line for C, dot for F, and then a line for D. And at the top, we've got C, F prime, and D. So this is showing that theta is going from the thing at the bottom, which is exactly the same as that, to the thing at the top. Now this is not terribly easy thing to draw, drawing a little dot in the middle. So in fact, in practice, what we do is we don't replace our 2-dimensional blob in the middle by a dot, by zero. We actually enlarge the book. So right like that. So we have a theta. So this is the basic thing. We rewrite all things of that form in this form, and as I say, diagrams go upwards and from the right to the left. So what can we do with these? Well, we can compose in various ways. So how can we compose? We compose natural transformations in two ways. We can do, as we've seen before, the way you stick two functors together. So we can, if we have natural transformation phi from G to G primed, and this is going from D to E, and we have theta going from F to F primed, and we have a C here, then we just draw this by gluing the two pictures together. So that's going to correspond to a picture in string diagram language. That just looks like phi here and a theta here. Okay, and if I just stick the labels on for you, a G, an F primed, a G primed, and we have three regions. So the regions correspond to the categories C, D, and E. So often it's convenient to miss out the labels depending on how obvious it is where things are coming from and going to. So that's the one composition. This is the composition for the functorial direction. We can also compose in the natural transformation direction. So we can compose two natural transformations. So in that case, we would have something like a diagram like this. So we would have theta primed and a theta going from, theta goes from F to F primed, squeeze that on, and then theta primed is going from F primed to F prime primed, and so F is supposed to go from C to D. So we're going from C to D. Okay, so we just draw that by sticking the two things on top of one another. So in this case, we have something that looks like this. We have theta primed, and we have a theta, and we can label these F, F primed, F prime primed. And this goes from C to D. So this is just telling us we've got two natural transformations which are composable along the source and target, the target of that one compared to the source of that one, and we can just glue them together. Okay. So that's the basics, but we can get more advanced than this. What can we do with these? So I could draw you a picture of some ways of composing things. So if I just drew you a picture like this, and if we suppose that this is C, this is C, and this is theta, and we have D here and E here, and we've got an F, a G, an H, and we've got a, remember the notation from before, I usually use a slightly different notation. So this is just the identity functor from C to itself. So this is supposed to correspond to a natural transformation, which in old money we would write in the following way. So this is just C to C, and we've got a D. Ooh, running out of time here. So we've got a natural transformation theta from 1 on C. Now what we can actually do, what we tend to do here is, if we've got this identity, we can actually remove it. And so we would just draw it like that. We lose nothing by removing it. So I'll tell you what this has to do with monads next time, and we'll start seeing some more exciting things. Okay, so this time I'm going to carry on with some string diagrams. So first, a little bit more about the generalities, and I think I've said too much possibly already about the generalities, and I should just get stuck into some examples, but just a little bit more before I do. So we've got the notion of the interchange rule for composition of natural transformations. So if we have 4 natural transformations, and hopefully I've drawn these sensibly here. So we're going from category C to D and then to E, and we've got functors f, f prime and f prime prime from C to D, and we've got natural transformations from f to f prime to f prime prime, and similarly on this side here. Then there's a couple of ways we can compose these. So for instance, we could stick those two together and stick those two together, and to get 2 natural transformations which we can then glue together horizontally. Or we could have done it the other way. We could compose those two together first, and compose those two together, and then glue them vertically. And the interchange rule for natural transformations, which is a calculation, shows that those two things are the same. So if you just glue, if I just stuck those together, I guess I could just do something clever, like remove those lines and those lines. So doing that, the interchange law says that's well defined. You don't have to specify which way I glue them together. So over in the world of string diagrams, remember we're taking duals here. So what we do is we have a little dot here, well, which we make a little bit bigger, and then we take the dual of that line becomes this line here, and the dual of this arrow here becomes this line here. And so this bit here becomes the bit over here. So I've just translated this picture into string diagrams. The interchange law says that this is well defined, so I don't have to specify if I'm doing horizontal or vertical gluings first. Okay, so that's the interchange law in string diagrams. One other thing I should mention is sort of the identity natural transformation, just how we notate that, which is sort of like whiskering in some sense, whatever whiskering really sort of means. So whiskering, I guess, in this globular language means we have some, try and draw my diagrams very precisely. Oh, I'm not succeeding. Okay, so we just have G and C, and we have a theta, say going from F to F primed, and the idea is we can stick on, if we have a functor G from D to E, then I can do this horizontal composition. What this G really means here, so this really means the identity natural transformation from G to itself. So that's what that G really means. But it's not really doing anything interesting, so we just write it like that. Okay, so how do we represent this over in the world of string diagrams? Well, we just do kind of the obvious thing. We're supposed to be taking the dual, so we just represent it by a straight line like that. So over here we have G, over here we have theta, and we have F primed and F, and you can either fill in what's supposed to go in the regions. You see, I'm not doing this very well at all. Let's put it up here so we don't confuse it with this G and this E. But the diagram can get a bit cluttered, so I'll often just remove these things. That looks a bit less cluttered, and hopefully it's still unambiguous. Okay, so this time I'm finally going to get to telling you about adjunctions and string diagrams. So up on the board, as I prepared earlier, here is what you had previously as a definition of adjunction. So 2 categories, functors going between them. We say F is left adjoint to G if we have an epsilon and eta, so going in these directions. So F and G is not symmetric in F and G. Remember, F is the left adjoint, and we've got to satisfy these 2 triangle inequalities. So what I want to do is show you how these triangle inequalities and these 2 natural transformations translate into string diagrams. So the first thing I want to do is just write these sort of a bit more globularly. So what we do is, so we have our epsilon is going to be a natural transformation. So this, so we have F from G, and 1 on D, going from D to D. And similarly, eta is going to be going to do F first, and then do G, and it's coming from 1 on C. And now we have to translate these into pasting diagrams. So you saw very quickly how that happened previously, so let me just explain that, take a little bit of time to explain that. So what we've got the equality of two, this diagram commutes, says that two natural transformations are equal. So here, we're not going to express it as a commutative diagram, but as an equality of two globular things. So what we have to do is we have to start with F and apply F eta to go to FGF. Now, eta goes from 1 to GF. So I guess secretly I should be sticking on a little 1C there. It just makes sense if I just put that there for now. So that's going from F1C to FGF. So let's just write FGF. That's going to be the middle bit. So we've got F, G, F, G, F. Oh, I want to draw this much further out here. So what have I got to do? I've got to just do nothing on F and apply eta. So eta was this one. So what I want to do is apply eta going upwards, and this goes to 1C. So here we've got the first bit. We're going from 1C composed with F to FGF. So that's the first bit. That's that bit of the natural transformation. Then we do this bit. So we do epsilon on the first two. So we glue this bit on. So we want an epsilon on here, and we just do nothing. We just stay with F. So that's the composition of the transformations along the top, and this is just 1 on F. So that's supposed to be equal to the thing, of course, in this whiskering notation we just write like this. So that's just F. So this is just supposed to be that represents the identity natural transformation on F. So that's how we translate this into globular things, and we have a similar interpretation on the other side. And can I do this without going through it slowly? Let's possibly not. So I can probably do it slightly quicker. So this is G, F, G, and it should be obvious from here which has to go on where. So on the top we have a G epsilon. So that must be an eta, and that must be an epsilon. So that's a 1D, and 1C. And that has to be equal to just doing nothing on G. So this has to be this. Going from D to, going from C to D. I'm going from D, to C. Which means I've got that label on there. Now I want to tell you what this is in the string diagram language. So what do we do? So remember the key was take duals of things. So we're supposed to replace this globular thing by a dot. Well, in fact, I said replace it by a circle. So we're going to replace it by a little circle with epsilon. This is just the identity. So we're supposed to replace this line by line here, but it's just the identity. So I'm just going to put it dotted at the moment, and then I take the dual of these two things. So I'm going to replace that picture by that one, and similarly this picture by something. So I couldn't quite draw those in the middle because those arrows are in the way. That's the only reason. So let's just a little bit of space on the bottom. So to specify an adjunction, I want to specify a natural transformation line. So this is just going to be eta. So what I should do is draw it as I said. So this is epsilon. So this should go from GF to identity. But what I said is we're not going to draw the identities because they do nothing. So composing with the identity does nothing. So in fact we can quite happily remove that. And to tidy up the notation a little, we're actually not going to bother writing the little epsilon in there. Whenever we see that, we know this is going to be an epsilon. If whenever we see a little cap there, we know that's going to be our epsilon. So similarly for eta, you do the same little thing, and this is going from the identity on C, which we just leave, to something from F to G. And sitting inside here, of course, the thing in the middle here is C, that's the category C, and this region here is the category D, but you get the opposite way around here, we get D inside and C on the outside. So, how do the triangle equalities look in this picture? Right, so if we do the duals here, so we sort of have a dotted line there. We just draw the duals here. That's equal to that. So remember, we're just drawing the identity as just a straight line. So when we write this down in the string diagram picture, what we see is that if we do a little wiggle, we can pull the wiggle out. Like that. And let me just label this correctly for you. So we've got an F, a G, no, sorry, we don't have G up there, we have an F up there, and we have a little G in the middle here. So we go from F to FGF, just to F. And this is just the identity on F. So these pictures just equate to this very simple diagram here. So you do exactly the same thing here. We do draw the dual. Here, so this says that if we do it the other way round, so we just put the cup here on the left, so I should have said cup and cap, it's supposed to be a little cup and this is a little cap here, so the other way round, it is saying that this little wiggle is equal to a little unwiggle. We just pull the line straight, so that's just the identity natural transformation on G is equal to the thing you got if you'd gone from G, applied the unit, and then applied the co-unit on the other bit. Oop, a little bit of coughing in the audience there, it wasn't me. So, to sum up, in string diagram notation, what is an adjunction? An adjunction is supposed to be given by a natural transformation, well, a pair of natural transformations and a pair of relations, which satisfy a pair of relations. So all we do is we just specify our natural transformations in the following diagrammatic form, and according to the laws of string diagrams, the relations just are specified in this fashion. And I'm out of time, and next time we'll have a look at how adjunctions relate to monads in this string diagram notation. Okay, so this time what I want to do is tell you about monads in the language of string diagrams, and then hopefully, if I've got time, we'll see how you get monads from adjunctions via string diagrams, and then that's where things really kick off. You see, that's where I really understood what monads and adjunctions were, was when someone showed me the string diagram notation, and things just clicked for me. So it's not necessarily the notation for everyone, but it's certainly the notation for me. So let's just crack on and have a look at monads. So recall that we have a monad is if we have a functor t from C to C together with two natural transformations. We've got mu, the product or multiplication, natural transformation from t squared to t, and eta, which is the unit, which is natural transformation from the identity on C to t. And it has to satisfy, well, these have to satisfy two relations, and these two relations are, I guess, triangle equalities. So not triangle inequalities this time, as I was so fervently saying last time, and also this associativity. So we'll see these unital things and this associativity square in terms of the string diagram. So what have we got? So we'll translate this into string diagram. So we've got a functor t, and we've got two natural transformations. So let's just write these two natural transformations down. And I realised I've not been terribly clever with my board space here. I should have pushed that a little bit down. So let's just be stupid and draw these two natural transformations in the gap here. Okay, so we've got a natural transformation from t squared to t, which we call mu. So we have, draw a little box here. So mu, we're going to draw as a little thing that goes from t to t. So again, as this is the only sort of trivalent little blob we get, you'll often just erase the mu. It's usually clear from the context. So whenever I see that, that's my product. So this is a natural transformation. Mu and my eta. So what's eta? Eta goes from the identity functor to t. So I'm just going to draw this little blob here. So remember, identity functor we just draw as nothing. There's just nothing there. You can draw this little dotted line if you want, but it's not really worth it. And that's it for t. And everywhere kicking around, the only category inside here is C, so I won't bother writing these on. But you can put those on if you're worried at this point. As soon as you get fast at these things, you'll just ignore those. Right. So let's have a look at this picture here. So what's this say? So let's just take this left-hand triangle here first. And again, it's saying that two natural transformations are equal. If we do this one, or we do this one, then we've got to get the same answer. So the first one, it says we start, let's draw it up here. So we start at t, we just do t, but we apply eta. So we have to do one of those on the right. So we have a little eta. So that's the first natural transformation, and then we have to do mu. So we have to multiply these two together. So we just draw that, and that has to equal the identity natural transformation on the t. So get everything inside is a t. So I don't really have to label things. So that is equal to just do nothing. So what it's saying is you can absorb a little blob into the line. So if you have a little blob floating around, you can just get sucked in, or you can spontaneously just have one just hanging down there. So it's a sort of a topological move. For me, a topologist, that's a sort of a nice relation to have. And the one on the other side, so we're doing pretty much the same thing. We start with t, but we introduce the eta on the left this time instead of the right. So this is saying we start with a t, and then we just introduce an eta. So this is just eta t, the first bit, and then coming down, we're on t, so we've got t and t, and we just smash them together and end up with that. So that has to be equal to t. Now I don't know about you, I find that far easier to remember than that. But I'm sort of just visual, I guess. So let's have a look at the associativity thing, which seems to be not complicated, but again something quite straightforward. So we've got the equality of two natural transformations. We either go around the square at the top or along the bottom there. So always start off with three copies of t. So we go from t, t, t. And what do we do? So we just do nothing to the one on the left. So I'm going across the top here first. And we just multiply the two on the right together. That. And then what do? We just multiply the two things. Okay. And the alternative was to multiply the two things on the left first, just to go to t squared. So we've got two copies of t now as we're going up. So it just says these two things have has to be equal as natural transformation. So again, I put t's on everywhere, but you understand that there's t's everywhere here. So this is just associativity. I mean, this is just saying if you're multiplying the two things there and then multiply the result with the other one, it's the same as multiplying two things and then coming in from the right and multiplying the other one. So in our string diagram language, a monad is just some t, so I guess we could just say we've got a t like this together with these two natural transformations and these nice, easy to remember graphical identities that are satisfied. Okay, so if anyone's, I don't know if anyone's familiar with the language of sort of monoidal categories and has seen these sorts of pictures in monoidal categories. These are sort of the pictures for a monoid in a monoidal category, and there's a lot of similarities. Well, that's because we're working here with functors and natural categories, functors and natural transformations. Now that's a strict 2 category, and we're using this notation in there, or we could have sort of talked about monoidal categories, which is something completely different, seemingly. But these are both examples of something up here, which is the idea of a weak 2 category. So the string diagrams sort of naturally live in the natural notation for weak 2 categories, and monoidal categories and strict 2 categories, of which the 2 category of categories which we're dealing with here are both examples. So it is the same sort of language you might have seen before. Now, even if you haven't seen it with monoidal categories before, you've probably heard of Feynman diagrams. And these might look like Feynman diagrams to some of you. Well, that's because that's the stuff that's going on in monoidal categories. I mean, that is what Feynman was talking about, certain diagrams representing morphisms in monoidal categories. So that's really where the genesis of these things come from. So I've sort of waffled here a bit at the end. Now, as I said, I wanted to get onto adjunctions this time, but I've run out of time. But we'll see. What I'll do for you is I'll show you how we can get from an adjunction to a monad very quickly using this language. Okay, so this time I'm finally going to get around to showing you adjunctions, giving you monads in this string diagram language. So as I said before, I hopefully didn't overemphasize this, not over-egging my pudding here, this is sort of where we really see the utility of these string diagrams. I should point out, as I've been told I should point out, I mean, string diagrams are wonderful things, but it's only one point of view, and it's sort of my favourite point of view for doing things like that. But one of the disadvantages is you never see objects, so we're just thinking of categories, functors, and natural transformations as a package there. So we're not seeing any internal structures in categories. So we're just looking at sort of that as a 2 category, as we'll perhaps see later. So these kind of meta things, it's quite useful to do with these diagrams, but when you're actually crunching away at specific monads, this isn't necessarily so helpful. But to do this stuff, it's wonderful. Right, okay, so we're going to have an adjunction. So between C and D, we've got F and G. F is left adjoint to G. So what does that mean? It means we have 2 natural transformations. We have epsilon, which goes from Fg to the identity, eta going from the identity to Gf, and these have to satisfy these 2 relations, formerly called the triangle identities, not the triangle inequalities, but here they sort of attain new names for obvious reasons, either snake identities or the, well, it's not the wiggle identity, what is it? It's something like that, but I can't remember. It'll come to me in a second. Right, so we've got this data, we've got an adjunction, and we want to produce, from that data, we want to produce a monad. So what was a monad? So a monad was a functor on a category, together with 2 natural transformations, the product and the unit, which are going to satisfy some identities. And it's going to be obvious what these things are from this setup. So, well, you already know what these things are going to be, but what is our T going to be? So we've got to produce a monad T from a category to itself. Well, you know what it is. It's just GF. So this is one of what our monad is going to be. We're going to go F and then back to C. So this is sort of C, C. And we sort of nip into D in the middle. Okay, so what is our product going to be? Well, it's going to be pretty much forced on us as soon as we see what this product is supposed to be. So it's supposed to go from T to T. So what's T? So that's at the bottom. This has to be. I won't write it sufficiently big. So we do G, then we do F, then we do G, and then we do F, and we've got to go to G, F. Okay. So we're going to somehow build ourselves a natural transformation. Now, all the information we've got is these two things at the top here. That's the only natural transformations we can play with. So it's pretty obvious what a sensible thing to do is. We just use epsilon, standard problem, eta epsilon problem. That's an epsilon, a little cap there, and we just take sort of the identity on G and the identity on F. So there's not a lot else we could actually do there. Similarly, we're pretty much forced as to what we should take here. So we're going from the identity up to on C up to T, but T was just do G and then do F. And how can we go from there to there? Well, look, it's eta. That's essentially the only thing. So we define our product and our unit in that way. So what we have to check is that these satisfy our identities for a monad. So we had the unital identities and we had the associativity identities. So and they're just going to be ridiculously easy in this setup. So let's have a look. Which one should we do first? Let's go for the unital thing. So we had these two unital relations. You can remember them, which said, let's do this one on this side. So if we just have our unit and then multiply it in, then that's the same as doing nothing. So we need to show that this is true. Okay, so let's just expand out the thing we've got here. So the right hand side is equal to, what is this? So we start with a G and an F, and we put in a unit, so we just wobble this in here. Okay, so if I just put a dotted line across there, you can see that's what I've done. I've got identity and unit, and then I just do have the product, so it's just these two. But we've got this relation, which says this little snake relation says that we can just pull that straight. Okay, so this little thing here can be pulled straight. So by the snake relation or the triangle equality, this is just the same as. So what are we going to do? This bit here gets replaced by a straight line. Okay, but that is just the thing we wanted. So this is just a T. Oh, easy way to write that. So that's just a answer. So you see immediately that this is just follows straight from the triangle relation. Then we've got of course the one the other way around is exactly the same. Okay, and it's so exactly the same I won't actually draw it in. It's just going to use the other triangle relation. So we've got 2 out of the 3. So the other relation we needed to use, the other identity we needed to show was the associativity identity. So like that. And the associativity identity was just saying, let's multiply 2 things at the bottom, and then multiplying a third. Ooh. That's exactly the same as multiplying the 2 things and then at the bottom, and then multiplying the thing on the left. So is this true? Okay, so let's just have a look at what we've got. So the left hand side is going to be, just expand this out. I'm not exactly sure how big this bit. I'll just write quite long along the bottom here, so we get G, F, G, F. Whoops. Stick there. F, G, F. Probably didn't need to make it quite that big. So what are we doing? So we're multiplying these two together first. So we go like that. I've left myself enough room. And then we multiply these two together, so we just combine these, this F and this G, like that. Okay, so now we can just use the interchange law. So here we can just simplify this picture a little straighter. It's actually that. So we can use the interchange law to just alter the order in which these two natural transformations are done, because they're acting on two different things. So we just use the interchange law to move this one down and move that one up. So this is equal to the following. Is this going to look appropriate? Well, we'll see. So that, and that, so this is just the interchange. And we have F's, G's, F, G's, F. Is that right? GF, 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 GF. GF, GF. G, F, and that, of course, was just that. If you unplug this, this is exactly just do the little cap there, and then join the others with a little cap. So that's exactly the thing we have on the right-hand side. Okay, so out of time, and I've finished. Yes, so we see instantly that if we start off with this data, satisfying these relations, we find the monad in this way, then it automatically, just for obvious sort of topological move type reasons, gives us a monad.